Okay. I'll have your exams for you on Monday. It's been a bad week. They're still the same place they were on last Friday, so unfortunately nobody's asked me how they did. So I'll have them for you on Monday. I may post the answer key today, but they'll definitely be done on Monday. Okay, so to finish up reactions of aldehydes and ketones. So what we've done so far is we've made hydrates, we've made acetals, we've made hemiacetals and hemiketals and acetals and ketals, and we've talked about how they're used for protection, how they're used for sugar. And so now let's move to a nitrogen as our nucleophile. And the thing with nitrogen, using an amine, for instance, is that it doesn't need acid. Because on the periodic table, remember we've got CNOF, that as we go from right to left, we're increasing the nucleophilicity. So nitrogen is a stronger nucleophile than oxygen is. And so it doesn't need the acid. And even if you did add acid, you would screw things up, because if we added H plus to this reaction, the nitrogen, being a stronger base, would become protonated, and it's no longer a nucleophile. It's an electrophile. So we don't use acid. We can just go ahead and use nitrogen, and it's strong enough to add to the carbonyl all by itself. And so that's what's going to happen. But before we get to that, we have to define amines. And the next chapter is on amines as well. So there's primary, secondary, and tertiary amines that are based on the number of alkyl groups attached to nitrogen. So if a nitrogen has 2 hydrogens and 1 alkyl group, it's primary, 2 alkyl groups secondary, and 3 alkyl groups tertiary. I can't add a tertiary group to a carbonyl, to an aldehyde or ketone, and we'll see why in this mechanism. Okay, so here's what happens. If I react an amine with a ketone or an aldehyde, I'm going to make this molecule, which is called an imine, or it's also called a Schiff base. And I'll explain why it's called, the technical difference between the two of those. So let's talk about that one first. And unfortunately, so how do we form imines or Schiff bases? So if I take, and this, I'll do this with a ketone, and I'm going to add to it a primary amine. The primary amine is going to come in, attack the carbonyl, and have the pair of electrons go up there. It can do that on its own because it's a strong enough nucleophile. So I end up with this species that has both a positive and a negative charge. I'm not sure if the term Zwitterion, bless you, if Zwitterion is still in vogue, but that's a term that we can use for something that has a negative and a positive charge in it. Now, that molecule's not going to want to stay in its ionic form, so the hydrogen is going to transfer from the nitrogen to the oxygen. Sometimes people will just write that with the arrow here, showing that it'll pick up the hydrogen from the nitrogen, so I'll end up with an OH, and now with an NHR. That's okay, but realize that that's probably not what's happening. Because probably what's happening is that the O- on one molecule is picking up a hydrogen from another molecule. Because again, it's not just individual molecules like we write it on the screen. So now I'm at this molecule. And so what happens is that this undergoes an elimination. And it's going to eliminate water. And the one thing that happens with this reaction is normally it's done with heat. So otherwise it's kind of hard to imagine this step happening. But what's going to happen is this pair of electrons is going to go here to form a nitrogen double bond. And then the OH is going to leave. And we know OH isn't a great leaving group, but under heat, the H plus off the nitrogen, and the OH will leave as combined water, and we end up then forming a double bond to the nitrogen. And you could say, well, what about the acid? Couldn't acid protonate the OH and make it leave as water? There is no acid, right? Because we said at the beginning there can't be acid because of the that would kill the nitrogen. It would turn it into an electrophile. So this is the commonly accepted mechanism for imine formation. This molecule right here is called, well, it's not technically an imine, it's technically a Schiff base. So a Schiff base has a C double bond N with an R group over here. If I did this whole process with ammonia, then I would end up with what's truly called an imine, which is an NH, because that came from taking the ketone and adding ammonia to it. So this is truly what you would call an imine, although we use that term interchangeably. So an imine comes from ammonia, and a Schiff base is just a normal run-of-the-mill molecule. Okay. So overall, then, there is an equilibrium here. And that equilibrium is to take the ketone, react it with the primary amine, and that is in equilibrium with the final product, and water. And so if one was going to do this reaction in the lab, there's a couple, you have to somehow push the equilibrium to the right. And that's done commonly one of two ways. One way is to remove the water as it's formed. And the other way that's done, which we don't have any real control over, but just happens, is that a lot of the Schiff bases or imines that we form are actually solids, and so they precipitate out of the solution. And so if they precipitate, they're basically pushing the equilibrium to the right as well. So this is addition followed by elimination of water is the term. So does that kind of make sense? But this only occurs with a primary amine because, as I'll show you in a minute, I need to lose one hydrogen. I need to transfer one hydrogen to the O-, and then I need to be able to lose one hydrogen to get the double bond. And so when we go to a secondary amine, I only have one hydrogen overall. And so that's going to get transferred I have nothing to form the CN double bond. So I've got to change the mechanism a little bit. So that's forming imines and Schiff bases. And again, imine comes from ammonia. A Schiff base comes from everything else. Now let me go back here. There are lots of classical imines and Schiff bases that we can make. Again, primary amine does not make an imine. It makes a Schiff base. NH3 makes the imine. And then classically there's been a lot of compounds that are similar to this. A hydroxylamine looks like this. So that if you take a hydroxylamine, you'll end up here with the N attached to the OH. And that's called an oxy. And then if you take 2,4-dinitrophenylhydrazine, hydrazine has an NH2 attached to another NH2, or NH attached to an NH2. And my structures are all messed up because because somehow PowerPoint ate them. But if you do this phenylhydrazine, and hydrazine is N2H4, that's what we used in the Wolff-Kishner reduction. But when we attach a 2,4-dinitro phenyl group, we end up forming then the 2,4-dinitrophenylhydrazone. And let's see, over here there is an NO2 group. Then you could also make semi-carbazides by taking this NH2 attached to an NH attached to carbonyl and NH2. And that makes what's called a semi-carbazone. Right. Why are any of these important? Well, they're not as important as they once were. Right? For those of you in lab yesterday, I told you about my sad second semester organic lab experience where we were given, for the second half of the semester, we were given 4 test tubes of unknown compounds, and we had to figure out what they were. We had no NMR, a really old IR, and we had to do all the chemical tests in order to figure out what our compounds were. That it wasn't just 4 hours a week, it was any time you had free time, you were in the lab trying to figure these things out. Okay. Woe was me. We don't do that as much anymore because of spectroscopy, we can get all that information. But there was a time when you had to do chemical tests, what are called qualitative tests, in order to determine the identity of a molecule. So you would start with the idea of what functional group do you have. If you thought you had an alcohol, you would take a small amount of sodium or potassium metal, add it, and if it fizzed, it was an alcohol. If you had a ketone, if you thought you had maybe a ketone or an aldehyde, you would add one of these reagents, either the hydroxylamine, the 2,4-dinitrophenylhydrazine, or the semi-carbazide. Usually it was the 2,4-dinitrophenylhydrazine, because when you added that to an aldehyde or ketone, it formed this compound, which was a precipitate, and its color was anywhere from red to orange. So if you thought you had an aldehyde or ketone, you would add that compound, and if you got a precipitate, then that would tell you you had an aldehyde or a ketone. How you differentiated between those is coming up. So that red-orange precipitate, or whatever color it was, we would recrystallize it and we would take the melting point of it. Because just like in lab this week, you made the 3,5-dinitro benzoate ester. There were books that had all the aldehydes and ketones in them, and they would have the melting points of the 3,5 or of the 2,4-dinitrophenylhydrazone derivatives. So by knowing the melting point or the boiling point of the ketone or aldehyde, you would then look across and say, oh, well, here's the melting point of the 2,4-dinitrophenylhydrazine derivative, and so I think it's that one. And usually it was never enough to just do this once. You would do it with the semi-carbazide, and that compound's melting point was there as well. So if you did 3 of these and you got the same melting point, or the melting points all matched up, you could pretty much say, that's my aldehyde, that's my ketone. And so pre-spectroscopy, that's how you would determine the identity of an aldehyde or a ketone, is by making the hydrazone or oxime or semi-carbazone as what we call a derivative, and then taking its melting point. We don't do that as much anymore, although still in my files I do have a qualitative analysis where we would give you a test tube of unknown and you'd have to figure out what it is. And you could do a mini version of this, not 8 weeks, but a little bit minier. So that's why these things are important, or that's why these things were important, is because we could do that. The driving force then for each one of these compounds is the fact that they would precipitate from solution, and that drove the equilibrium to the right. Okay. Right. And shift bases are still used as ways to make molecules that are ligands for different metal ions. And so you can make the shift base and have it bind to like a copper. And that copper complex might be used as a treatment for, maybe an anti-tumor or some type of treatment. If you could get that inside the cell, it might destroy a cancer cell, or probably any cell to begin with, and then you'd have to tune it to just do cancer cells. So that's where the imines and the shift bases come into play. It's addition, elimination. Right? Everybody kind of with me on that? So now let's do that. Now let's change the molecule from a secondary, or from a primary amine now to a secondary amine. And so this is going to change the second half of the mechanism. So my first step here is going to be to do what? Have the nitrogen attack the carbon of the carbonyl. So same first step. Bless you. To form this bitter ion. And the next step is going to be transfer the proton from the N plus to the O minus. And now I'm stuck, because I don't have a hydrogen attached to the nitrogen to eliminate. But this is still an addition-elimination reaction. And technically this is called a hemi-aminal. I didn't know that until a few years ago because one of my former colleagues was having a research student try and actually make what I'll show you, the enamine, in a minute, from trying to react a certain type of secondary amine with a ketone, and couldn't get it to work. And after they were in my lab, just round bottom after round bottom of brown tarry stuff, I'm like, well, maybe we should try a different approach. And we tried a different approach, and we got this compound with an OH and an N in it. And I'm like, okay, what is that called? Because it's not, I never teach it. So it's called a hemi-aminal. So what am I going to eliminate? Let me write down here. Let me put a CH2. Let me expand out that group. So what happens is that if I can't eliminate from the nitrogen, I'm going to eliminate from a carbon. And so the carbon, if the carbon next to the carbonyl has a hydrogen, in my elimination step, I'm going to lose that hydrogen and the OH. So the net result is I'm going to lose water. But now what I'm going to do is form a double bond to the carbon that was attached to the carbonyl. And this is called an enamine. So let me rewrite the structure. Can everybody see why this is a enamine? Remember this? What was that? That's an enol, because it's half alkene, half alcohol, and so this is an enamine. Same principle, half alkene, half amine. And when we get to enol chemistry, or actually we'll deprotonate this and call it an enolate, we'll come back to this because they do very similar things.
Is there a way of choosing like which R group would form the double bond?
Yes and no. Right now, if I had two molecules, so this is a question I like to ask sometimes. So we know this is secondary amine, and so when I write, I'm going to have an N with my two R's, and I'm going to have my double bond either to carbon A or carbon B. So can we choose? Yes, but only one of these we would know how to make now. So which one of those two, where would the double bond go? To carbon A or carbon B? What do you think? How many people say A? How many people say B? Why B? It's more substituted, so if we put the double bond to carbon B, we would end up with a more substituted double bond. So could I choose? Yes, but it's made for me. If I want to form the less substituted double bond, I'm going to have to do something different. So right now we're kind of locked into forming the most substituted double bond. And because this reaction would involve heat, and remember, I'm also forming water, so in other words, to push this equilibrium to the right, either this thing has to precipitate out of solution or I have to remove water. I'm kind of stuck. Because under reflux conditions, that automatically sets thermodynamic conditions. So I'd automatically get the most stable product. For enolates, I do have a choice, but we'll get to those later. Okay. So this is the difference between a secondary amine and a primary amine. Primary amines form the CN double bond. Secondary amines form a CC double bond. And they form the enamines. And again, what are these useful for? When we talk about enolate chemistry in a few weeks, they can do that. They can do those kinds of reactions. They can also become ligands as well. All right, everybody kind of with me? Okay. Other reactions of aldehydes and ketones. What's called the Wittig reaction. W in German is a V. So this is the Wittig reaction. Another Nobel Prize winner, George Wittig, who came up with this. And so what this allows us to do is to couple two parts together. One part coming from the ketone and one part coming from what's called an ylide. And we couple those two parts together, making a double bond. So the overall approach here is kind of like what we talked about with Heck coupling or Suzuki coupling or Gilman reagents. I'm going to create the two parts and I'm going to attach them together. And not only am I forming a carbon-carbon bond, I'm forming a carbon-carbon double bond. And so that's why he won the Nobel Prize for this. So how do you make the ylide? Well, to make the ylide, what you do is you take triphenylphosphine. So we've briefly saw triphenylphosphine in, I believe, Heck coupling. Phosphorus is below nitrogen on the periodic table, so it's a better nucleophile than nitrogen. So what's going to happen is the triphenylphosphine, the phosphorus will come in and attack this carbon. This is supposed to be a CH. And kick off the bromine. So I end up with my triphenylphosphorus attached to my carbon. And then the bromine is the counterion to the phosphorus. So I've now formed a phosphorus carbon bond. Okay, and so the next step then is to deprotonate that CH using butyl lithium, which is C minus with an Li plus. I could use really any C minus species here. Lithiums are easier to use than Grignards. And butyllithium is a reagent that's used. You can buy it in bottles. They ship it around the country in tanker car quantities because it's used for making rubber. It's used for doing these kinds of deprotonations. It's a fairly important one. But the C minus will come in, and the C minus will deprotonate that CH, leaving you with a C minus. Okay. So first we had the triphenylphosphine, and then I deprotonate the carbon to make this that now has a plus charge on the phosphorus and a minus charge on the carbon. And then this bromine should be gone. Then what happens is, and you could probably write the double bond between the carbon and the phosphorus, but then this is what's called the ylide. So there's an E on it. So the ylide then reacts with the carbonyl, and it goes through a four-membered four-sided intermediate. And so if you think about a pair of electrons on, well, actually this, the double bond, the CO double bond is used to make an OP bond. And then this negative charge on the carbon is used to form the CC bond. So that I just made the CC bond, the PO bond, and I now have a square intermediate. This is called an oxyphosphate, or it's also called a butane. Do you have to know all of these things? No, but I'm just showing you how we get the product we get. So then what happens is then this isn't very stable, and so it reacts so that we break the carbon-phosphorus bond. This pair of electrons comes down to form the double bond. This pair of electrons goes up so that I form a triphenyl phosphorus with a double bonded oxygen. And that's called triphenylphosphine oxide. It's insoluble, so it just precipitates out of solution. And now I've ended up coupling the part from the alkyl halide to the part from the ketone. And why would this be important? Because if I wanted to put a double bond in a really complicated molecule, I would have one team generate the ketone part. I'd have another team make the alkyl halide part. I would use then the Wittig reaction to couple those two parts together. And there's probably rules on, am I going to get the E or the Z isomer? So I could probably do it fairly stereoselectively. But that's what the Wittig reaction does. So how would you write the Wittig reaction? How would I write it? I would write it taking a ketone plus an alkyl halide, and then I would say 1 triphenylphosphine, 2 butyl lithium, 3 there is no 3. and I would couple those two parts together. So that's how we would do a Wittig reaction. So examples of Wittig reactions, I just showed you one. And there'll be more in the homework, in the kind of homework problems. I'll show you another one. If I wanted to make that compound, and I said, hey, start with cyclohexane. It's a lot of steps to make that molecule from cyclohexane, because I'd have to put this entire part on the cyclohexane, probably using a Grignard. But if I just said, okay, I'm going to take my cyclohexane and I'm going to free radically halogenate it. And then I'm going to react that with my number one. I'm going to react that with my triphenylphosphine. 2, I'm going to react it with butyl lithium. 3, I'm going to react it with what's called methyl ethyl ketone. It's got a methyl on one side and an ethyl on the other. In those 3 steps, I would then end up coupling the ketone part to the alkyl halide. So as long as I can make the alkyl halide, as long as I can react that with the appropriate ketone, then I'm done. Does that kind of make sense? This one is kind of a memorization. Triphenylphosphine only does 2 things: Heck coupling and Wittig. So when you see triphenylphosphine, that's the only two things you can do. All right, what else do we have? And this is just like a hodgepodge series of reactions, but they're all important to make or to do reactions with alkene or with ketones and aldehydes. All right, so this one is Baeyer-Villiger Oxidation. And so in Baeyer-Villiger oxidation, I'm going to react a ketone with a peroxyacid. That's what this is. So we've used peroxyacids before. If I had 5 or 10 minutes for you to flip back through your notebook and tell me, I'd ask. Could anybody remember how we used peroxyacids before in less than 5 to 10 minutes of notebook flipping? To make epoxides. So the role of the peroxyacids is to add an oxygen. First, it adds the oxygen to the double bond to make the epoxide. What's going to happen here? What's going to happen here is it's going to take that oxygen and it's going to add it in between the carbon and the alkyl group of a ketone. So over here, what I'm going to end up making is I'm going to make an ester. And where will that What side of the ketone will that oxygen add on? It's going to add on to the side with the larger group. So if I took something like that same methyl ethyl ketone and said I'm going to react that with peroxy acid, I would end up inserting an oxygen on the side with the ethyl group. So I could turn methyl ethyl ketone into ethyl acetate. Which is a neat trick. But doing this with acyclic ketones is pretty boring. Because where this really becomes important is if you want to make cyclic esters. And if I was smart, I would have had an empty slide after that. Bless you. Cyclic esters are called lactones. And if I wanted to make a lactone, what I would need to actually make two functional groups on the end of a carbon chain and try and have them wrap around and add to each other. So maybe make something like a hemi-ketal here with an OH, and then oxidize that OH group up to the ketone. That's not going to work. That's going to be really difficult. On the other hand, if I take something like cyclopentanone and I react it with a peroxy acid, I'm going to insert my oxygen in between the carbon and the CH2 group, and I'm now going to expand the ring 1 and make a cyclic ester, the lactone.
What happens if there's a functional group on it? Why does that change? Is that symmetric? So it would add if they affected the same product.
Right, and the only thing I would add to this is if there's like a methyl group on one side, the oxygen would go to the bigger of the two groups. If there's another functional group in the molecule, I got to be really careful because I don't want the peroxy acid to oxidize it. But if I had this molecule, for instance, and said, okay, let's go ahead and react this with my peroxy acid, I'm going to end up then with a 6-membered ring, and the O is going to be here. The O will add to the carbon that's the bigger group. So you have a little bit of control. And with all these reactions, these are sort of the generic ones, and then people modify these to have more and more and more control. And we don't ever get to that point. We just, the bigger types of reactions. So that's the real importance of Baeyer-Villiger is to make cyclic esters. Because it gives you the ability to do it in one step, whereas otherwise you've got to close up the ring and all sorts of things that aren't probably going to work. So that's Baeyer-Villiger oxidation. Now, I'll put in the folders these two tests. So I talked about, there are color tests for aldehydes and ketones, but how do you determine whether you have an aldehyde or a ketone? There's two more color tests that specifically are for aldehydes, and one of them is called the Tollen's test. So in the Tollen's test, what we do is we react an aldehyde with silver, ammonia, and hydroxide. And this only works with aldehydes. So what this does is this oxidizes the aldehyde to a carboxylic acid, but since the solution is basic, the carboxylic acid is deprotonated. And that's great. I mean, this is very specific for aldehydes, so if I had two functional groups in the molecule that would react with an oxidizing reagent, if I just wanted to oxidize the aldehyde, I could use Tollens. The key part is what happens to the silver, because the silver gets reduced from silver 1 to silver metal. And so if you do this reaction in like a round bottom flask, if you keep swirling the solution around, eventually the inside of the round bottom flask gets coated in silver. Right, so you can make a big Christmas ornament. Except you only have one color, silver, because it's silver metal. And this is the technique that used to be used to make mirrors. If you took this reagent and put it over glass, you would silver the glass and make a mirror. Right, which is why vampires can't see themselves. Right, because to kill a vampire, well, let's see. Can you use silver bullets for that, or is that werewolves? Anyway, they can't see themselves because in the old days, all the mirrors were made of silver, and so they wouldn't reflect their light. I think. So that, but nowadays we actually just probably melt tin or something like that on it and don't do this because silver is expensive. And so I'll put a link to like a YouTube video where they do this. We used to do this with the little kiddies making like silver flasks that they could take home. So it's kind of a cool reaction. But what it does is it will be a test for aldehydes. It would also then be very specific to oxidize just aldehydes and nothing else. This wouldn't work with an alcohol. It wouldn't work with any other group that could be oxidized. And the last one that you may have done in biology class is a Benedicts test. And in the Benedicts test, it's the same principle. I'm going to take my aldehyde, I'm going to react it with a copper. I'm going to react it with copper 1 reagent along with hydroxide. And in this case, what I'm going to end up doing is I'm going to end up oxidizing the aldehyde to a carboxylic acid that'll be deprotonated. And I end up forming, this is copper 2 plus, and I end up forming a copper 1 oxide. Copper 2 is blue in color, if you remember that from General Chem. Copper 1 oxide is red, sometimes called brick red, because it's what the pigment they use to put in bricks to make them red. So if in biology you've ever done a reaction for a reducing sugar, a reducing sugar is one that is in its cyclic form, but there's a tiny bit of it in its open chain form. That open chain form has a free aldehyde. The copper will react with it, and so if you heat it with like a Bunsen burner, the blue solution will eventually turn red, and you'll see the red precipitate come out of it. So this is sometimes in biology a test for reducing sugar. But it's the same thing, we're oxidizing aldehydes up to carboxylic acids. Okay, so that's the end of aldehydes and ketones. And we've already done reductions of aldehydes and ketones, so. Okay, so on Monday what we'll do is we will, your problems are due, and we will also we'll start into amines and continue on.